Marcus cross-relationship probed by CDNP study of degenerate electron exchange reactions of short-lived radicals. This study explores how certain very fast chemical reactions, involving short-lived molecules called radicals, can be tracked and understood using a specialized technique called time-resolved CDNP. The goal is to improve how accurately scientists can apply a theory called the Marcus cross-relation, which helps predict how quickly electrons move between molecules during these reactions. By adjusting the temperature and precisely measuring how the reactions unfold, the researchers looked at a few specific chemical pairs, such as those found in guanosine and tyrosine, which are important building blocks in biology. With a sensitive NMR instrument, they were able to form and observe these radicals, studying how the reaction rates changed from very cold to hot conditions, 8 to 65 degrees Celsius. They then compared the actual measured results to what the Marcus cross-relation theory predicted. In most cases, the theory matched well with the experiments, but there were some reactions where the predictions were off by a large margin. The study also found that how quickly the magnetic properties of certain atoms changed during the reactions closely followed a well-known mathematical pattern as the temperature changed. Overall, this research demonstrates that time-resolved CDNP is a powerful tool for studying the ultrafast processes that happen when electrons hop between chemicals. This not only helps chemists test and improve theoretical models but also increases our understanding of key chemical steps that are central to processes in biology and materials science. Introduction. Chemically induced dynamic nuclear polarization, CDNP, was first discovered in 1967 during NMR experiments involving organic radicals. CDNP is valuable because it reveals information about short-lived radical molecules important in biological systems. This effect occurs when pairs of radicals undergo spin-related interactions, leading to opposite polarizations in their reaction products, helping scientists understand the formation and fate of these radicals. Electron transfer reactions, where electrons move between molecules, are described by Marcus theory. A special case, degenerate electron exchange reactions, D, involves molecules differing by only one electron. The Marcus cross-relation allows predicting the rates of such electron transfer reactions based on related reactions. However, this requires knowledge of certain constants that can be estimated if temperature-dependent reaction rates are known. The current study focuses on validating the Marcus cross-relation more accurately by measuring the temperature dependence of D rate constants between biologically relevant radicals, specifically radicals derived from guanosine monophosphate, GMP, and tyrosine derivatives. Studying these D reactions with short-lived radicals poses challenges because traditional optical and spectroscopic methods can't easily detect them due to unchanged reactant concentrations or very brief lifespans. However, the photo-induced time-resolved CDNP, TR-CDNP, technique enables detecting and analyzing these radicals using laser pulses and NMR signal changes over microseconds. Using TR-CDNP, the study examined the reduction reactions of GMP radicals by tyrosine-related anions in various temperature conditions, 8 to 65 degrees Celsius. The researchers determined parameters such as reorganization energies and compared calculated reaction rates from Marcus theory with experimentally measured values. While most results showed good agreement, a few electron transfer rates differed considerably, illuminating the limitations and accuracy of theoretical predictions. This research highlights the power of time-resolved CDNP to study ultrafast electron exchange reactions in biochemically significant systems and to refine theoretical models describing these fundamental processes. Conclusions. This research uses a technique called CDNP with very fast time resolution to study how electrons move between certain short-lived molecules called radicals. These reactions, called degenerate electron exchange, D, were examined for radicals derived from guanosine monophosphate, GMP, tyrosine, and N-acetyltyrosine in an alkaline water environment at temperatures between 8 and 65 degrees Celsius. By changing the temperature, the scientists measured how quickly these electron exchange reactions happen and calculated important energy values. They also directly measured one specific reaction's speed at 25 degrees Celsius. When comparing their detailed calculations based on a well-known electron transfer theory, Marcus cross-relation, with actual experimental results, they found good matches for some reactions but large differences for others, particularly for GMP radicals reacting with tyrosine and N-acetyltyrosine. These mismatches might be due to the models not fully considering some molecular effects like how molecules stack or the complexity of the electron transfer process itself. The study also looked at how the magnetic properties of certain hydrogen atoms in these radicals change with temperature. They found different behaviors depending on the chemical environment, showing that some atoms relax their magnetic energy through one mechanism involving movement of parts of the molecule, while others do so through the whole molecule's rotation. One type of radical showed a mix of these behaviors. Overall, this work highlights how advanced techniques like CDNP can reveal both the speed of electron transfers and physical magnetic behaviors in short-lived radicals. Understanding these details helps improve theoretical models and deepens knowledge of important biological and chemical processes where such radicals play a key role. This important article is authored by the following scientists: Thank you for watching this video. Please subscribe to our channel BP International to watch more videos in the fields of science, technology and medicine.